Today we are going to talk about the three-tank system. My name is Shahin Behnamian. My two partners, Kaveh, Zakerolhosseini, and Michael Stockbridge. Alright, to talk about this three-tank system and what it does. So it's a system that has three different tanks on three different levels. And what we want to do is monitor the amount of water level in every tank, and with that information, we're going to take the necessary actions required in order to keep every tank at the water level that we want it to be. So in order to do that, we're going to need sensors and pumps and valves. So say for example, there's water being consumed at this top level, and the tank is getting emptied out. So what we need to do is recognize this and start pumping water to that top tank. So how we're going to do this is we're going to start pumping water into this top tank from the second tank. And once we do this, we also recognize that this second tank is also losing water. So from there, we're going to start pumping water into this. And same thing's going to happen. And there's a big bottom tank that's going to serve as an outlet for overflow and water supply. So it'll work like a cycle. So the water will be going throughout the system. And so what we basically the main point is we're trying to take this physical information, turn it into digital data, and then with this digital information, we're going to have a logic that's going to decide for us what's the best necessary actions for us to put every level at the level that we want it to be in every tank. And we could say this project is an example of a control system. So there was certain things we wanted this project to be. We wanted to have a sturdy frame, so it won't be lagging back and forth. It'll be safe and standing at this place, even if it's pushed away or anything. We want appropriate sensors in order to tell us the water levels, which we're going to talk about what our solution for this is soon. We wanted one universal power supply. So we wanted one power supply that's going to provide enough power for the whole system. So as soon as we just plug it in somewhere, that's all the power we need. And we want it to be safe and durable. Say some wires fall into the water. We don't want the pumps to burn. We don't want the power supply to burn out. We want it to be safe. And we also want it to be durable so it'll last for a long time. We can keep that project on for hours and hours and then work fine without a problem. And basically we want a microcontroller to serve as the brain of our system. So the microcontroller is going to make all the decisions, therefore there will be no human interference required for our system at all. Alright, to get an overall view of our system, it's going to have the power supply. It's going to provide power to the level sensors and to the microcontroller, to the valve, and the pumps. So these level sensors, they're going to recognize how much water is in the tank. And with that information, it's going to send to the microcontroller. And the microcontroller is then going to decide which pumps to turn on and which valves to open. So, and just to let you guys know about our individual contributions, I'm the project manager. So as the project manager, I had to be involved in all aspects of the project. Everywhere from coming up with a logic for our code for the microcontroller, along to helping build the system, and along with meeting all the deadlines that we have set for our system. And Kaveh, Zakerolhosseini, he's our technical manager, and his main contribution to the project was programming the microcontroller. He was a programming expert, so we came up with logic, and he went to work on the coding part, and controlled the MSP 430 very well, so it worked very fine. And Michael Stockbridge, who was our financial manager, he kept track of how much we're spending and how much we had left in our budget. And he also built the system. He's very experienced with circuitry as a technician he's worked before, so we really had a good background to help us with this. And to the next one, I'm going to let Mike talk about the circuit part of our system a bit.
Yeah, my name is Mike Stockbridge, and like you said, I did a lot of the circuitry, and I did the plumbing, so I'm just going to go over the circuit diagram real quick. So the system pretty much just consisted of a power supply. We have these height sensors for the water, a microcontroller, we have some relays, valves, and pumps. So the power supply supplied 5 volts and 12 volts. We had a current handling capacity of over 4 amps. Then we had 2 valves. They're solenoid valves. They're 12 volt solenoid valves at 450 milliamps. And we had 3 pumps at the same thing, 12 volts, 450 milliamps. Now, they got their power from the power supply through the relays. A relay, they're reed relays. And the reed relay is pretty much just a coil and a switch. So you would apply a voltage across the coil, it would create a magnetic field, and that would close the switch, which would allow the 12 volts to go through a power. So over here we have height sensors, and the height sensors are pretty much whatever the height of the water in the tank, it would, okay, the sensor is just basically a variable resistor. So whatever the height in the tank is, it's going to produce, it's going to change the resistance. So with the 5 volts, we set up a voltage divider, which would in turn apply voltage to the microcontroller, and that would send an output out to the valves and pumps to the relays. So pretty much the way the system, if you fill up the water, you're going to get a signal to the microcontroller, output to the relay to the coil. The coil is going to energize, and then 12 volts will go through to the valves. And so at this point, I'm going to hand it over to Zach. He's going to talk more about the microcontroller.
Hello everyone, my name is Kaveh. I was mostly responsible for configuration of the sensors and programming the microcontroller. The microcontroller I used was MSP430. Language was based on C programming. I used 2 ports on it, port 6 and port 2. I used port 6 to read the data from the sensors, and port 2 to send the commands to the valves and pumps. Basically, there are 3 main parts in the programming. First part is configuration of the sensors and connecting them to the microcontroller and get the analog data converted to digital, and based on that, to do some processing. Second part is initial condition when all the tanks are empty. Since we don't want the pumps to be working at the same time when there is no water in the tanks, which would cause the pumps to burn. So we have some kind of program that when the water is at some point in the first tank, then we'll open up the second pump. And when the water is at some point in the second tank, then we'll supply water to the third tank. So we have some program for initial condition. And the last part is when all the tanks are full, and we apply some disturbances to the system, mostly the third tank, based on the requirement of the project. Level sensors that we have, basically they work based on the resistance of the water. They give us resistance between 300 to 800 ohms. And if you put them in series with 470 resistors, basically a voltage divider, they will give us the voltage between 1.875 to 3 volts, which is readable by the microcontroller. Since everything more than 3 volts is not readable by the microcontroller, so we satisfy that. Basically for tank 1 and tank 2, when the water goes below 5.5 inches, we will turn on the pumps and the solar valves above those tanks. For example, if water goes on below 5.5 inches in the second tank, we'll turn on the third pump and second valve. And for the last tank, third tank, when the water goes below 4 inches, then we will turn on and start the pump and the valve below it. And when it gets to the 5.5 inches, we will stop the whole supplying water to it. So we have some tolerance about 1.5 inches. And that's again based on the requirement of the project. And basically in tank 1 and tank 2, water goes below 4 inches, we won't supply any more water to the tank above it, because we don't want it to, want them to empty out, which again would cause the pumps to burn. And each tank checks its level every 10 milliseconds, so the program is timer based. Takes about 1 minute and 30 seconds for the whole system, all the tanks to become full with water from initial. And it takes about 4 seconds for the third tank to get full, get full or get empty about 1 inch. So we get some rate for the height, and based on that we get the formula for volume in terms of cubic inches and inch. Now I'm going to ask Mike to come back here and explain more about the future improvements of the system. Thank you.
So I just wanted to go over just briefly what some improvements could be made to the system. The way the system is at this point was made to the specs of the project, but these are some things that could be done in the future if we wanted to. We can replace the relays with H bridges, so that because ours are fixed operation, we can make it H bridges makes it variable operation. We can replace the high sensors with pressure sensors underneath the tanks instead of having. We can change the manual valves to solenoid valves. That way you could use the microcontroller to control all your dump valves. So more flexibility. Use a single MSP430 chip. So right now we're using an experimenter's board from 447, and we could just use a single chip, or we could use an Arduino or a different kind of microcontroller. And the last thing is LabVIEW. LabVIEW is a program that you could connect to the system so you could visually see, you could like make a control panel or something like that, then you have user interaction, the user could change, you know, parts of the system. So this is the funds that we spent. The whole project ended up being about around $800. We also had some of our sensors that were donated. They were $40 a piece, so it saved about $200. These are man hours, so all the productive hours, everything that was done for any, the microcontroller for putting the system together, for all the testing, that was pretty much 350 hours. The documentation and all the research, Shahin did a lot of the documentation, and we all did the research, 130 hours, about 380 hours or so. Or 400, sorry, 400. And at this point we wanted to show a video.
Okay, so here we're going to start when our system is empty. Completely all tanks are empty. Our microcontroller is going to recognize this. So we sped this up a little bit, not to bore you guys to death. Then the first tank's going to fill it up, and then once that has enough water in there, it's going to start filling up the second tank, eventually leading to the third. And finally, it's at the level that we all want each tank to be. And then we're going to add some disturbance to the system by opening up the first menu above on the top right. So once we do this, you're going to see the water's getting emptied out, and we want the system to use to recognize this and start pumping more water into it in order to have a steady supply of water. And as you can see this happening, the whole cycle with the left water pouring down into the big bottom tank. So then we open up the second tank, and what we're going to recognize is that this one right here, the water is going to get drained to below 4 inches. And as we have in our code, once it recognizes it has below 4 inches, the water is below 4 inches, it's going to stop supplying water to the third tank until it has enough water for itself before it starts pumping up again. And we'll see that right there. Once it hits at the desired level again, it starts pumping more water into the top tank. And finally, it'll be back at the equilibrium, at the level that we want it to be. And just to show you some more disturbances even to the first tank, immediately it's going to start recognizing it and start pumping more water into it. Get back to our PowerPoint. Along with the many technical things that we learned with these projects, such as figuring out the microcontroller, actually putting together such a big project and having enough voltage and current for each individual piece. This was really our first time working as a group with such a big project, and I feel like at first the communication between us was a bit off, but that's just what took us some time to learn, and once we got all on the same page, we started working together very well, built some good team chemistry, started counting each other, and have a good working project. And we're going to demo it today after the presentation on the second floor in the engineering building, so if you guys are interested to see this in action, you're very welcome to stop by. And a main lesson we learned is never assume anything. There were some logics that we came up with where we said, okay, when this is going to happen, this something else is about to happen. I'm not going to get too specific, we don't have time for that. But what we did is make sure you experiment first to make sure everything's going to work the way we want it to work. And we want to give special thanks to Dr. Girdler for helping us throughout the whole project. Even when we ran into brick walls, he always had his office door open for us. And he helped us really a lot to get on the same page and finish this project in time, and we met the deadline. And also to Dr. Cook and Dr. Guy for sitting through some of our presentations and giving us good feedback. The ECE department for letting us do this project. We really had a good experience and really worked well as a team. And Mile 1 Technologies for providing us the height sensors free of charge. They saved us a couple of $100, so we really appreciate them helping us out. Thank you. And right now we're ready to take some questions.